Okay, so for question 9, what I've done to begin with is just find the general Taylor expansion for cos of x, and that comes out as shown here. You could obviously find the various derivatives and so on. I just did it mentally. You could write them down to work that out, but hopefully you'll see that this is indeed correct. Okay, so we've got to show that essentially our series will converge to cos x for all values of x, and what that really means is we need to find the error term and show that the error term will tend towards 0 as n tends towards infinity. Okay, so let's have a see how we're going to achieve this. The first thing to notice is that if we consider the derivatives of the function, I've written it down as the n plus 1th derivative evaluated at t. I'm not quite sure I've put a k in there, they should be t's as well. Nonetheless, what we can then claim is that we'll always get a derivative which is either plus or minus, it should be sine t, or plus or minus cos t. So we can now say that the error term will be given by this for some value of c, and if we split this up as follows, what we can now say is that in fact our error term will always be less than the modulus of x minus a to the power of n plus 1 over n plus 1 factorial, and that's simply because our derivative, regardless of where it's evaluated, will always be less than or equal to 1. So now what we've got to consider is the limit as n approaches infinity of x minus a to the n plus 1 over n plus 1 factorial, and what we're going to see is that we get the limit as n approaches infinity of the error term is going to be less than or equal to 0. I've put a little asterisk here because I'm going to discuss how we could prove that in a second. But obviously the error term being a modulus of the function Rn x, it will always be greater than or equal to 0, and so by the squeeze theorem we can now say that the error term is indeed 0 as n tends towards infinity, and that completes that proof. Okay, let's just have a look now at how we could prove more conclusively what happens here. The first thing I'm going to do is just define a new variable, a large x, to replace that x minus a, just for reasons of simplicity in writing it out. So what we're interested in is now the limit as n goes towards infinity of this expression, and if we think what this actually looks like, we could rewrite this as shown, where I've defined m to be an integer which is greater than x. You could say it's the next integer that's greater than the modulus of x, and m of course will be less than n plus 1. Now what I can therefore say is that this will be equal to k times by the modulus of x over m times by all the terms in between, and at the end times by the modulus of x over m plus 1. And so essentially what I'm doing here is saying that from modulus of x over 1 times modulus of x over 2 all the way up to modulus of x over m minus 1, that's just going to be some constant or other, given that m is some integer value. Have a think about that. Okay, so what I can now do is replace all the denominators on the right hand side with m, and given that I've lined these up in order of size, hopefully you can see that that will be true. M is the smallest possible denominator from those remaining terms, and hence the division by that will give you the largest possible amount, so we get this inequality. I've now just tidied that up and said it looks like this. If you think there should be, you should be able to see there are n plus 1 minus m of these terms all being multiplied together, and then I've gone on again and I've broken this up into these two parts. Now what I'm going to do this time is look at the second part, which says you've got the modulus of x over m to the power of 1 minus m. And again, if you think about it, for any given value of x and m, that will simply be a constant, and if I times that by k, I'm simply going to call it the constant p now, and so I get this expression. And what I can now claim is that this statement will be true, and furthermore, I can say that the limit as n goes towards infinity of p times by the modulus of x to the n over m will equal 0. And the reason behind that... there's one slight error here. Let me just try and correct that right now. This should be... Hang on, I've needed an extra bracket in there. That should, of course, have been like this. Okay, that's more like it. And of course, because m is bigger than the modulus, m is an integer greater than the modulus of x, then that's a fraction that's less than 1. And as n tends towards infinity, of course, that tends towards 0, like so. And then we can use the squeeze theorem to finish off this result. And that's it.